5.5, the substitution rule. In this section, I just want you to keep in mind what we're going to be doing is taking the antiderivative of a chain rule. This slide says our antidifferentiation formulas don't tell us how to evaluate integrals such as the antiderivative of 2x root 1 plus x squared dx. Our strategy is to change from the variable x to a new variable u. This is called u-substitution. Okay, so we're doing u-substitution. And you'll hear me say u-sub a lot. What I mean by that is we're going to find the function and then we're going to find its derivative in here. And so let's take a look at the next slide. Let's try and evaluate this by setting some u, and we should see the function and its derivative in there. So for this one, I'm just going to tell you that u is this. What's underneath of this root is the u. So we're going to say, let's let u be 1 plus x squared. If I let u be 1 plus x squared, then du would be 2x dx. Another way to think of this would have been we were taking the derivative of u with respect to x and we got 2x, or we could just put it like this, because in the next step we're going to do our u substitution. So we're going to rewrite this as, you see this is now my du. Let me just rewrite this function for a second. So it's a little clearer. We have 1 plus x squared to the 1/2 power times 2x dx. I just reordered things. And that is the antiderivative of u to the 1/2 times, this whole thing is du. Well, now we can do it. The antiderivative of u to the 1/2 is add 1, and then we get 2/3. Don't forget your plus c, because this is an indefinite integral. And then we just go back and we know that u was 1 plus x squared, u to the 3/2 plus c. So I think that by just doing this example, having you look through it, you'll start understanding what we're doing. And then the next slide says it very well. In general, this method works whenever we have an integral that we can write in the form f of g of x times g prime of x. So this is just a chain that we have, and we are going to undo it. What pops out at you that might be our u? Hopefully this is popping out at you. Let's try it. Doesn't always work, but let's try it. Let's let u be x to the 4th plus 2. Well, then du would be 4x cubed dx. Do you see a 4x cubed dx in this? Let's just rewrite this, how we're hoping for it to work out. Just reordered things. So no, you don't see a 4x cubed dx, but you do see an x cubed dx. So let's just say, well, 1/4 du equals x cubed dx, right? And so now we can substitute in all the x's. We want to substitute u's. So we can't just substitute some u's and have some x's. No, we want to change all the x's to u's. So we get the antiderivative of cosine, that's just u, times, and this thing here we said was 1/4 du. Just going to pull the constant out because you can always do that, right? And the antiderivative of cosine is just sine. Don't forget your plus c. and then go back and put in your x's. So u was x to the fourth plus 2. The main challenge in using the rule is to think of an appropriate substitution. You should try to choose a u to be some function in the integrand whose differential also occurs, except for that constant, or some complicated part of the integrand, perhaps the inner function of a composition of functions, which we just saw in the last example. What do you think the u might be? Probably what's under this root. So let's try it out. Let the u be 2x plus 1. Then our du is just 2 times dx. We had the antiderivative of, that's just u to the 1/2 times, oops, we just wanted a dx. So we are going to have to divide both sides by 2. And so we can substitute, instead of dx, we can substitute in a 1/2 du. Take that constant out. Add 1. So divide by 2/3 plus c. So we have 1/3. Okay, I just multiplied these. U, which is 2x plus 1, to the 3/2 plus c. Alright, in this one, what do you think you want u to be? Probably what's under the root. Let's try it out. So du is going to be negative 8x dx. So let's rewrite this guy. So I'm going to rewrite this as x times 1 minus 4x squared to the negative 1/2 dx. What I'm really hoping for, this is my u, and so I want this part to be part of my du. So I'm just going to reorder things. I want my x dx. I need to substitute for that with a u. So I'm going to divide both sides by negative 8. Now I can substitute. This was just u. Take out your constant. Okay, add 1. So then I'll need to multiply by 2 plus c. So I get negative 1/4. My u was 1 minus 4x squared plus c. And that's it. Now, in this case, what do you think the u is going to be? Let you think for a second. Hopefully you thought to yourself, let's let the u be the 5x, because I know how to take the antiderivative of e to the x. So I know how to take the antiderivative of e to the u. So let's let u be 5x. Then du is just going to be 5 dx. So I can rewrite this as e to the u. Oops, I don't have a 5 dx. So I know that 1/5 du equals dx. Pull out that constant, and then I get 1/5. The antiderivative of e to the u is just e to the u. Okay. This is a difficult one. Find the antiderivative of tangent x dx. I don't even know what to do here. So the only thing I can think of is that tangent can be rewritten as sine over cosine. Now I'm stuck again. I haven't taught you how to undo a quotient rule. All I've taught you is the u-substitution, and that's the name of the game in this section. So I'm going to want to do a u-substitution. Probably don't know where you're going right now. Let's see, we could rewrite this as and make sure you write cosine of x to the negative 1. Remember, this is not the same thing as, because that's arc cosine, so just remember they're not equal. Anyway, probably by writing it like this, I just gave away what the u and the du was. Because by looking at it like this, what do we have? This should be our u, and hopefully that part's going to be our du. And so hopefully you're seeing that. U is a cosine, du is a bad sign. I didn't want a bad sign, I just wanted a sign. So I'm going to divide both sides by negative 1. Now I'm going to do my u sub. Well, if you need to write this out for yourself, go ahead and put it in the order that you need it. Because I now see that this part is just negative du. This part is just my u. Let's pull that negative outside. What is the antiderivative of u to the negative 1? Remember, if I added 1, I would get 0, and I can't divide by 0. So remember, that's the one that is ln absolute value of x. You must know that one. And u was just cosine. Up until now, we've done a bunch of indefinite integrals. Now we must do definite integrals. The tricky thing here is that the 0 and the 4 are my x bounds. So if I were to change everything into u's, these would still be left as x's. I know they look like numbers, but they are corresponding to my x's. When I change things over to u's, these no longer make any sense. So there's two different methods. One method is to first evaluate the indefinite integral, and then to go back and substitute the x back in like we've been doing, and then to evaluate it. So what I mean by that is to go ahead and just do it like we were doing it back in the previous example, and then not to substitute any values in until we get to this point and we change everything back to x's. But another way is to change my bounds into u bounds. And this is my preferred method, and I'm sure this doesn't make any sense at all, this slide, but when I show it to you, it's going to make a lot of sense. So let's go ahead and do this one by changing the limits of integration. And what I mean by that is change these from x bounds into u bounds. So in order to evaluate this integral, we've done it before, but let's just do it all over. We let u be 2x plus 1. And then we let du be 2 dx. So then we rewrote this as we had the integral u to the 1/2 times, and we just wanted dx, so we needed to make this into 1/2 du. And so we had times 1/2 du. Now, I didn't put my limits of integration here yet because we don't know what they are. All right, first we were saying when x was 0, what is u? This is what u equals. When x is 0, what is u? U is 1. When x is 4, what is u? Nine. So, since I have all u's, I must also have u bounds. So my bounds are going to be 1 to 9. So now when I do this problem, I do the same thing that I did before. Take out a constant. Take the antiderivative of that. But now I don't do the plus c because I have a definite integral. I'm going to evaluate this between 1 and 9. I'm not going to go back ever and substitute in my x, because if I did, then I would have to go back to these bounds, which would defeat the purpose. What I'm trying to do is simplify my life here. I've changed all my x bounds into u bounds, so I don't need to get any complicated function. So now I just have 1/3 u to the 3/2 evaluated between 1 and 9. Just going to pull the 1/3 out. You can or you don't have to. Square root of 9 is 3. 3 cubed is 27. I get 26 thirds. Let's try it again. What do you think we're going to make u? That's always the key. Probably this. Let's let u be 3 minus 5x. So then what is du? Negative 5 dx. So let's rewrite this as the antiderivative. We're not going to mess with bounds quite yet. We have u to the negative 2, right? U to the negative 2 times dx. If you need to rewrite this for yourself. So I want just dx. I'm going to divide both sides by negative 5. Now what are our bounds? When x was 1, u is 3 minus 5, negative 2. And when x is 2, what is u? Negative 7. So we're going from negative 2 to negative 7. What jumps out at you? Hopefully it jumps out at you that this number is bigger than this number. Play with that in just 1 second. Let's just first take out our constant. So if you'll remember from the previous section that the integral from a to b of f of x dx is the same as negative b to a of f of x dx, because I'm going in the other direction. Just go ahead and do the same here. So we'll switch these bounds to negative 7 to negative 2, and we'll multiply by negative 1, so I just get a positive 1/5. Now take the antiderivative, so add 1, and evaluate that between negative 7 and negative 2. So I'm going to just pull that negative 1/5 out. And so then you stick in a negative 2. Negative 2 to the negative 1 is just negative 1/2 minus negative 1/7. So we have negative 1/5 times negative 1/2 plus 1/7, which is 5/14. So negative 1/5 times negative 5/14, and so we get 1/14. Wow, there's a lot of examples in this lesson. I'm getting tired. Alright, let's try and evaluate this one. Well, we see that we could rewrite this as 1e ln x times 1/x dx. So we have to think to ourselves, which one do we want to make the u? The ln x or the 1/x? You have to think which one's the derivative of the other. If I let u be 1/x, then du would have been, so if I let u be 1/x, then du would have been negative x to the negative 2, which you don't see here. So that can't be right. But if I let my u be ln x, then the derivative of ln x is 1 over x dx, which I do see here. Perfect. Okay, gonna leave off my bounds for a second. I get u times du. Couldn't be nicer for you. All right, these are our bounds. Let's play with them. If x is 1, then u equals ln of 1, which is 0. If x equals e, then u equals ln of e, which is just 1. So this problem, which looked difficult, becomes one of the easiest ones we've done. The antiderivative of u is just add 1. Done. Okay, one last thing. We can use the substitution rule for definite integrals to simplify the calculation of integrals of functions that possess symmetry properties. So, if our function is even, then we know that the antiderivative from some negative a to a is just going to be 2 times whatever the integral from 0 to a was. Right? Because this area is going to be equal to that area. If it's even, then we have symmetric over the y-axis. If it's odd, this one's really helpful. The antiderivative from negative a to a, when odd, you know that f of negative x equals negative f of x. So everything that was up here is down there. And so the antiderivative from negative a to a is just going to be 0. Because everything that was up here gets canceled out by the symmetry over there. So we can't always determine that our function is definitely even or odd. Sometimes it's neither, and so sometimes things just don't work out so well. But let's see if we can find any symmetry in this one. Well, we have x to the 6, so right off the bat we think it might be an even function. Maybe you're not sure, so you just check it out. Well, f of x is just x to the 6 plus 1. What is f of negative x? Negative x to the 6 plus 1, which is negative x to the 6 is just x to the 6. Okay, therefore it's definitely even. So instead of doing this, we can rewrite it as 2 times 0 to 2. Antiderivative of that, we don't need a u-sub or anything here. The antiderivative is just 1/7 x to the 7th plus x. Don't forget the antiderivative of 1 is x. Alright, in that one, by determining it was even, it didn't really help us a whole lot. In this next example, something good might happen. We really don't want to take the antiderivative of that, do we? Since we're going from negative 1 to 1, we're going to keep our fingers crossed that perhaps this function is odd. Let's check it out. F of negative x equals tan negative x over 1 plus negative x squared plus negative x to the 4th. Hopefully you remember that the tangent function is odd. The tangent of negative x is negative tan x. If you don't remember that, you should be able to think it through. Okay, and so this is negative yay, it's odd. Our integral is 0. No work. Now, do I expect you to really identify that? No, not from the get-go, but you'll see where it comes into play, and you'll be able to identify these when you need to. Anyway, I think that was a long enough lesson. That is the end.